Residential electricity is typically supplied through centralized grid systems operated by utility providers. In most regions, households rely on a fixed infrastructure that includes transmission lines, metering systems, and monthly billing based on consumption. For many users, this arrangement is largely passive. Electricity is available when needed, and costs are reconciled after usage occurs. Alongside this standard model, there is a long-standing interest in reducing reliance on centralized energy sources. This interest often increases during periods of rising energy prices, grid instability, or regional outages. In response, several alternative approaches have become common. Many of these alternatives are effort-intensive. Solar power systems, for example, usually involve site assessments, permitting, roof or ground installation, inverter configuration, battery considerations, and ongoing maintenance. Backup generators introduce additional requirements, such as fuel storage, noise management, mechanical upkeep, and periodic testing. Off-grid systems often require careful load planning and technical understanding to remain functional. A recurring friction point across these approaches is complexity over time. Initial setup frequently requires specialized knowledge or professional installation. Long-term use may involve monitoring, repairs, or adaptation to environmental factors such as weather, wear, or component degradation. For some users, the operational overhead becomes the primary obstacle rather than the concept itself. Within this broader landscape, a separate category of products exists that presents itself as simpler in scope, emphasizing minimal infrastructure and reduced technical involvement. The Energy Revolution system is presented as a digital instructional product. It is not a physical device shipped to the user. Instead, it consists of written materials, commonly described as manuals, schematics, and component lists, intended to guide the construction of a small electrical apparatus. The system is framed conceptually as a self-assembled energy device, drawing inspiration from historical electrical concepts attributed to Nikola Tesla, particularly coil-based designs. The materials typically reference early electrical experimentation as contextual background, rather than as a modern engineering framework. The scope of the product is limited to instructional guidance. It does not include hardware, tools, or pre-assembled components. All physical elements are expected to be sourced independently by the user from general electronics suppliers. The conceptual framing avoids detailed scientific explanation. Instead, the emphasis is placed on the idea of leveraging known electrical components in a specific configuration. The presentation positions the system as distinct from mainstream renewable technologies by focusing on small-scale construction rather than infrastructure deployment. Use of the Energy Revolution system begins with reading and interpreting digital documentation. This includes reviewing diagrams, parts lists, and assembly instructions. Time investment at this stage depends on the user's familiarity with basic electronics and schematic reading. Construction requires hands-on assembly. Users are expected to obtain components, prepare a workspace, and physically assemble the device according to the provided instructions. This process involves manual interaction, basic tools, and attention to detail. It is not a plug-and-play system. Once assembled, the system is described as static in operation, meaning it does not require ongoing interaction during use. There is no software interface, monitoring dashboard, or automated adjustment process described. Any repetition of use depends on rebuilding, modifying, or maintaining the physical setup. Environmental requirements are minimal in terms of space, but the process assumes access to a safe, indoor, or sheltered area suitable for electrical assembly. No specialized environmental conditions are specified beyond standard safety considerations for working with electrical components. The Energy Revolution system aligns most closely with individuals who have a higher tolerance for manual effort and a preference for building rather than installing infrastructure. It may appeal to those comfortable sourcing parts independently and following schematic-style instructions. The format favors users who value simplicity of concept over system depth. There is no layered configuration, optimization software, or scalability planning built into the product's structure. The appeal rests on reduced system breadth rather than technical expansion. Conversely, the product is less suitable for those who prefer fully integrated solutions or professionally supported systems. Users who expect turnkey installation, automated regulation, or long-term service frameworks would likely find this format misaligned with their expectations. It may also be rejected by individuals who are uncomfortable working with electrical components, or who prefer solutions validated through standardized engineering channels and regulatory oversight. When compared to solar installations or generator systems, the energy revolution system occupies a different position. It substitutes infrastructure complexity with assembly effort. Where solar systems trade higher upfront coordination for long-term automation, this product trades automation for manual construction. The system emphasizes consistency of setup rather than customization. There are no described options for dynamic adjustment, scaling logic, or performance tuning beyond physical modification. This positions it as a fixed configuration approach rather than an adaptable energy platform. In contrast to energy solutions that involve contracts, permits, or integration with existing utilities, this product remains self-contained in scope, relying solely on user execution of instructions. The overall trade-off is clear: reduced institutional complexity in exchange for personal involvement and limited system depth. The product remains defined by its instructional nature and the effort required to translate documentation into a working assembly. Its role within the broader energy landscape is narrow, positioned between conceptual experimentation and practical infrastructure, without extending fully into either domain.